Okay, I'm Tom Schutt. Welcome to Physics 221, Modern Physics. Hope you're all in the right place. So this is the contact information. I have an office right down there. Although if you actually want to find me, you'll have to find me in my lab, which is down on the first floor. I don't have any fixed, sorry. And this information is in the syllabus, and I didn't bring copies yet today. However, if you just copy down that URL, it's an internal physics page. You can get to it. That's where we're going to communicate with you over the year. And the syllabus is up there already. Okay? So this is really the one thing you need to write down. Okay, but coming back, if you really want to get hold of me, I'm in my lab. I don't have fixed office hours, but more or less you'll be able to just send me an email. We can set up a time. I'll be more than willing to meet with you. An important part of the class is the recitations taught by Pete Kiernan. Those are at the end of the week. Oh, I don't have the date time up here, but it's in the syllabus, and you guys must know it. I think it's Thursdays. And those are sort of a problem-solving session, right? So I will explain somewhat how to solve problems as the course goes on. But this part of the class, the lectures, are going to be a little bit more in the theory, and he's going to be helping you with the homework sets. The homework sets are going to be due on Fridays. There will be no homework set this week. But I'll give you one. I'll probably pass it out Wednesday, and it'll be due the following Friday. And then after that, they'll be due on Friday. Okay? We'll have, well, it's going to be set in the syllabus. There will be, I think there are going to be 2 exams in the final, if I remember right, but what's in the syllabus is what the answer is, plus the breakdown of the grading between homework and exams. Like any other physics class, you have to keep up on the homework, right? So, you know, don't fall behind. If you do have trouble at the beginning, make sure you're getting help. Get into the recitations, get into CME. You don't want to fall deeply behind, just like any physics class. In fact, you're general in college, and especially, and also definitely in physics, as you go further and further, the penalty for falling behind gets steeper and steeper and steeper. Unfortunately, we had a bit of a meltdown in the supplementary instructor. We thought we were going to have, just like last Wednesday, he evaporated. And so we haven't found the new person yet, and we may or may not. If not, that's unfortunate, but we'll see. I'm working on that. Okay? So any other administrative questions? Okay. Now, most of the class is going to be chalkboard, sort of standard, but today is kind of a bit of a show. It's an introduction to the subject. You can take notes as you feel like, but don't feel compelled to write any of it down because, you know, I'm just going to go through. Try to give an overview of what we're going to do for the rest of the semester and point out some, I think, some interesting things. Okay. So the first slide is sort of the background of this class. You know, where we are, where we were before what we'd call modern physics, end of the 19th century. And in principle, this is what you guys have studied up to this point in your previous 2 classes. Hard to see. Try to stand out here and use this pointer. I mean, really, it's fairly incredible what had been accomplished with physics. The mechanics, right? Going back to the time of Newton. I found this little figure on the web last night. Newton had drawn that. Here he was explaining the idea that the way you should think of an orbit around a planet was that if I launch a ball at a certain speed, it's going to hit the dirt. If I launch it faster, it's going to go further. And if I launch it at the right speed, the curvature of gravity is just going to make it orbit. And he wrote that down in 1665. I mean, the amazing thing about Newton, and I know you know this, but I just want to repeat it, is that here's this guy in England, and it's not him alone, of course, obviously. He's building on a long history, going back quite some time. Galileo had an incredible amount to do with it. But there they were. There was a person in the 17th century in England, and he writes down some equations. He invents calculus when he was in his 20s, and some other things, but he writes down these equations that describe orbital motion, and that means that as soon as you knew the distance from the Earth to the Sun, and you knew how long the Earth takes to orbit the Sun, which you know, the mass of the Sun was measured. Okay? I mean, just to think about that as a sort of a fact that mathematics describes the world and an intellectual achievement, right? And of course, a huge number of things follow from that. I mean, people had machines before that, but before you could calculate what you were doing, before you had calculus, I mean, how did you make progress? So, you know, there's a huge impact the mechanics have had. When I was a kid, we had a book, 500 Minds That Shaped the World, you know, sort of coffee table book. I don't know where my dad got it somewhere. Number one that was listed in that assessment was Newton. I remember that very clearly. People like Muhammad was number 3 or 2, you know, but Newton, number 1, according to this one guy's assessment. And you had electricity and magnetism. It led to electrical power and lighting. This is 1893 exposition where in Chicago, where one of the earliest places, times when they, sort of like the Olympics this time, but here what they were showing off is that we can have light at night, okay? And by in the 1830s, you had telegraphs out of that. Late 19th century radios, then television. I mean, a huge impact, right? And, you know, towering achievement, Maxwell's equations explain all of this, right? Thermodynamics. I think that's kind of a sleepy subject. Huge impact. You know, the notion that there's energy and that energy is conserved and that heat is a form of energy and it flows around. These are not obvious things. There were competing theories before it sort of all got sorted out. This is very subtle. The second law of thermodynamics, which is a very strange law, talks about irreversibility and entropy and stuff. Much of this is worked out. A person named Carnot. Basically, they were able to figure out the ultimate efficiency of engines. What was driving it was steam engines. Here's a 1788 Watt. Took a big step in terms of perfecting steam engine. That led to the Industrial Revolution. You know, let's use our brain power to systematically harness energy. And then let's think through how you're going to do that. What's the mathematics behind it? And that there is a mathematics behind it. It's not just trial and error, right? So this had a really huge impact, ideal gas law, right? And I don't know if you've heard this. It was widely discussed. Actually, sometimes I think people nowadays overplay this. Maybe it wasn't so widely discussed, but it's often pointed out that there were at least several prominent physicists in around 1900 who said that physics is done. All that's left is mopping up. Okay, we've essentially written everything down that there is to know because, my gosh, they figured out all this stuff. And it didn't appear that there were that many things that were measured that they didn't have an explanation, but there were some nagging questions. Actually, what's kind of interesting is that the couple of nagging questions that everyone did know about that were fully well acknowledged are fairly obscure. I mean, how many of you know what that statement is? Does anyone know what that really fully means? A couple of you have heard of it. That was one of the that was one of the main problems with what people thought they knew about the universe in 1900. They didn't understand the calculation of the Blackbody spectrum of objects. In particular, there was this thing called the ultraviolet catastrophe, which I think sometimes people say that'd be a good band name. The other thing was that there was this theory of light traveling through something called the ether, but no one could find the ether. Okay? So those are pretty obscure things. I mean, 99.99% of the population has probably heard of neither, and yet there were people who thought we understand all of the universe except those two things in 1900. But there were other examples, and I don't know, I'm not a historian of science, sort of armchair historian of science. I'm not sure how many of these were recognized or not, but they're definitely, in retrospect, many other questions that weren't known. In fact, some of them are so blindingly, it's like you didn't see your nose for your face, the nose at the end of your face. What underlies chemistry? Why do we have a periodic table? Why does anything have a color? Why is your shirt red? If you thought about it, they had no idea. None. It didn't make the list of the top 2 things we don't understand. What powers the sun? That's kind of important, you know? But it's almost like it was so basic and so much a part of our lives that they didn't even, I mean, whatever, I've said this, okay? What are atoms made out of? It turns out we did know about atoms, and I'm gonna come back to that point. What really is temperature? Turns out it's pretty subtle, what really is temperature. Equivalently, it's the question is what is entropy? There are other things. Boltzmann actually did understand it in the 19th century, but not many people accept it as explanation. Okay, so kind of I'm developing a theme here. It's that there's stuff that you can see and stuff that you can't see, and that, well, I mean, things are sometimes interesting. Okay. Often what is really not understood is right in front of us. And often it's the opposite too. Especially, I think it was the case in a lot of ways that what is understood is in fact a little bit obscure and remote. Okay, what do I mean by that? Let's look at electricity and magnetism where you have Maxwell's equations. You know, and that's fantastic, right? You guys have seen them, right? And you worked out and it's like, this is what light is. I mean, I don't know. I still get goosebumps thinking about it. I hope you guys think it's neat that there's, we can understand all that. But what are the physical manifestations of electricity and magnetism? I mean, it's kind of fleeting and unfamiliar. If you go to a science museum, you rub the fur on the amber rod and it makes a spark, I mean, this kind of, it's not very impressive in a way, right? There was lightning, people had crude batteries, but in fact, I mean, electricity underlies all of, chemistry, but not in a way that you can get your hands on. You don't see electromagnetic forces very often. I mean, nowadays in a modern house, sure enough, you want to go shock yourself, okay, there's real electricity there. But we don't see it very often. And certainly if you look back when they figured it all out, it wasn't like gravity, I mean, people weren't walking along and stumbling into a Coulomb. I mean, it just didn't happen, right? But nonetheless, there was essentially a complete understanding by 1861. Okay, that's kind of neat. Chemistry is sort of the opposite. I mean, chemistry, I'm a physicist, and especially when I was in school, I didn't like chemistry. I've grown to really like it, but I mean, it's incredibly important, right? For thousands of years, I mean, everything, it's what how our bodies work. It's, in practical terms, cooking, ceramics, metallurgy, right? And what did people actually deeply understand about it? I mean, it turns out we don't know anything about you don't really understand chemistry until you got quantum mechanics, okay? And they didn't have any notion of quantum mechanics at 1900. So, listing the various bits, chemical reactions, there were tremendous advances. Chemical reactions were beginning to be understood. The fact that there must be something like atoms was beginning to be understood. The ideal gas law fit in the periodic table. Again, but late 19th century. Okay, but the understanding arose only slowly, and there was no basic underlying theory. Okay, so now, eventually then, around this time, people began to understand that there were atoms. So first, the fact that there were atoms came from chemistry, right? That certain sorts of reactions only made sense if you had this sort of notion of elements and that these reactions are going to combine two of those with one of these. Therefore, there ought to be a fundamental building block. And that led people to realize that there must be some sort of fundamental thing, atoms and molecules. Okay? Then, and this I'm sure you didn't realize, there's the development of statistical mechanics, which is going to be one of the main topics. First off, I wouldn't be surprised if most of you have never even heard of statistical mechanics. Who's heard of it? Okay, who hasn't heard of it? Yeah. Okay. It's one of the basic parts of physics, and we're going to talk about it a lot. It was developed in the late 19th century, and it doesn't even work if you don't have some notion of atoms. So in fact, that was one of the underpinnings. If you say, when did we know there were atoms? It's kind of a fuzzy story, but this is one of the real ways at least scientists knew. And it's not what you're expecting. Another one was a biologist, Brown, in 1827, observed the random jiggling of dust in water. Okay? Dust particles in water. If the dust particles were small enough, and he was definitely looking under a microscope, he saw that they were randomly always jiggling. And of course, you've always heard that, temperature is due to the random motion of atoms, but you've never seen that. And indeed, we can't see atoms, right? Not with visible light, nor even molecules. But these are things that are much, much, much bigger than a molecule, but they're not that big. And you were beginning to actually see the motion due to this random motion. And he saw it for the first time, did not know what it was. Turns out Einstein figured this out a century later. It's called Brownian motion, not explained for a century. And putting it all together, in fact, a lot of times people say Einstein's figuring out of Brownian motion cemented, that was the final nail in the coffin that said there are atoms. Okay? And that's writing down what I just said. But still then, once you were at that point, the structure or substructure of atoms is completely unknown. Neutrons, protons, electrons, right? So what is this course? So this course, we're going to do statistical mechanics, quantum mechanics, relativity, and all of these are needed together to fully understand even more modern topics, well, certainly things about atoms, but then even, things beyond atoms. Cosmology, particle physics, modern material science, what's called condensed matter physics, okay? So we're gonna put all this together. And I guess what's interesting, again, just to reiterate one last time, is that while in the 19th century, it seemed like things were complete, the things that we had complete knowledge of, again, were somewhat indirect. And some of the stuff that's most basic to us, just, why is this table a table? Why does it act like it does? What gives us chemistry? All these things, that turns out, need this modern physics. And so it's actually in this modern era, and these topics, statistical mechanics, all three of those topics, are kind of strange and non-intuitive. Statistical mechanics maybe less so, but it's very mathematical, very abstract. And yet it's those things, these modern topics, which actually describe the world around us. It's almost as if physics developed backwards. The things we develop first were the things that are the most remote from us, except for gravity, obviously. But otherwise, the things that matter the most to us, or the most tangible and relevant, are the most obscure and the most difficult, okay? And that's what we're going to be doing in this class, those topics, okay? Not trying to say this class is going to be hard. It's just that these topics are a little more strange and a little more mathematical than what you've studied so far. Okay. So what is statistical mechanics? Okay. So basically it's, instead of talking about one particle, I shoot a cannonball, as you did in mechanics, and where does it go? We write down F equals ma. If you wanted to talk about air, as you know, in I think 22 liters of air, you have Avogadro's number of particles, 10 to the 23rd. So you're going to write down 10 to the 23rd F equals ma's, number them 1 through 10 to the 23, and start to solve? No, of course not, right? It's completely crazy. A set of people in the late 19th century developed the notion that actually, if you're going to describe something with a huge number of particles, all I really need to know is I need to know about the energy of those particles. Like for instance, if there's potential energy against gravity, mgh. And then I need to think about just the mathematics of probability for large numbers. Okay? And in fact, I just need a certain idea that if I have a large number of particles, they're just going to behave randomly. And so what actually happens is whatever is the most likely thing to happen if everybody just behaves randomly. And the classic and very simplest example is, suppose I take the room and I divide it in half, and I take all the air atoms, all the molecules of air, and I say, randomly, will they all be sitting over on one side, or randomly, are they going to be distributed throughout the room? And the answer is overwhelmingly, they're not going to be sitting on one side. You can calculate the probability that just randomly, through all their random motion, you'll happen to have them all have raced over to one side of the room at some moment in time. And it turns out it's fantastically unlikely. If you wait the lifetime of the universe, or you wait the lifetime of the universe to the Google, okay, it's not going to happen, all right? And so it turns out you can develop this and more rigorously And that's the field of statistical mechanics. So in fact, you can derive all of thermodynamics by looking at a statistical way, just like, let's just say stuff, I have a lot of particles, they're all just going to behave randomly, and they're going to do what they're going to do just according to that. One of the basic notions you come up with is that there's got to be some probability that if I have a bunch of particles and they all have some energy, the total energy is E, there's got to be some probability that they'll be in some state. And if the state has an energy, and you do not have to write this down because you're going to see this again, okay? If the state has some energy E, there's this beautiful and famous result due to Boltzmann that the probability of you attaining the state that has energy E, if the system is at a temperature T, is this strange beast. It's an exponential to the power energy over temperature with a constant out front called Boltzmann's constant. Okay? So it basically says, well, let me start. Just think about the math a second. If energy gets bigger and bigger, this exponent to this e to the negative of that thing will get smaller and smaller. This says that the system will favor states that have lower energy, all things being equal. Okay? And not just that it'll favor it, it gives me a mathematical way of talking about how much it favors it. And that's a profound thing. Actually, there's a huge number of results of just behavior of the world that come from that Boltzmann probability. And then there's another piece that goes along with it is the notion of entropy. So entropy is this sort of fuzzy notion of randomness. And it's got actually, turns out, a very precise mathematical definition. And I basically put this up here to kind of wow you, all right? You know, I mean, just, it turns out that entropy, there's a thermodynamic definition which has to do with the change in heat divided by temperature. Okay, and you may have seen that. But there's a much more, there's a statistic, it turns out there's and that was known for a long time. But what is the change in heat divided by temperature? It turns out that it's the same as mathematically this thing here. This constant again, the same one that appeared there, Boltzmann constant, times the natural logarithm, okay, of omega, where omega is the number of states available to the system. And that's a very subtle and very mathematical statement. But to give a simple example, and it's different in all sorts of situations, in our room right now, omega would be, if I had you guys get up and then all sit in different seats, and then we counted all the different number of ways you guys could sit in different seats. If you've ever seen this sort of thing, it's like combinatorial stuff, you know, how, you know, I make you two switch and then I make you three switch, and we do all that. There's a very precise mathematical way in any given situation to count the number of ways the system could order itself. And that's where we get the definition of entropy. Okay? And it turns out that, you know, you can take that as a starting point and derive all of statistical mechanics just about. Boltzmann was an interesting guy. He, this is his grave. There's a tomb, this lighting isn't great. In the back of his tomb, I wonder if I can get the lights darker here. Oh, yes. And back, don't go to sleep. On the back of his tombstone, you see it says S equals K log. Instead of omega at the time, they called it capital W. He had that put on his grave. He actually developed all of this and basically was, the scientific community rejected it. He couldn't get accepted and he committed suicide. But in fact, he had, you know, 20, 30 years later, people realized he was right. And it turns out, temperature, one of the most familiar concepts. I remember when I was an undergrad, and I was up to my junior, I was about to take my senior in college, and I had a roommate who was, you know, off sequence from me. While we were living together in the summer, he was taking the sort of junior/senior level StatMech class. And there's one here, okay? And, you know, we were talking one day, we were geeks, and so I was, you know, he's telling about the class, and I was realizing, you know, I've never seen a definition of temperature. You know, energy, 1 FMV squared, or MGH for, you know, a given situation, right? Where have you seen a definition of temperature? This is the temperature of the thing. If you think about it, you actually have, there's kind of some indirect things. In this situation, the temperature is related to an energy change through heat capacity. But that's not a definition of temperature. Turns out the mathematical, rigorous, modern understanding of temperature is that 1 over kT is the derivative with respect to energy of the logarithm of the natural log of the number of states. And I remember he told me that, and I thought he was screwing with me. We got in my roommate, because he was taking a class where he'd learned that. And I just couldn't believe that something as fundamental as temperature could possibly have some weird, bizarre equation associated with it, what actually defines it. But that's actually the mathematical definition of temperature in a given situation. Very strange, right? Even though temperature is so common, right? We all know what temperature is. And it turns out that, and we'll develop this a little bit later in the class, that it's an interesting thing, what the temperature means at a statistical level. Okay. Interestingly, and why did I talk about statistical mechanics first? It's not actually the first thing we're going to talk about in the class. We're not going to spend a lot of time on it, actually. But one of the reasons I presented it is that's almost it's kind of historical. Statistical mechanics was developing. I mean, actually only a few people were really working on it, Boltzmann and a few others, partially in obscurity. But they actually, this direction of looking at things turns out was one of the things that led to understanding quantum mechanics, of all things. So how did that come about? One of the, okay, well, what are you going to do with statistical mechanics? I mean, so one thing I said is it actually gave us for the first time a real mathematical definition of temperature. But it did other things. You can calculate, well, you can go back and you can understand thermodynamics at a more basic level, and there's various sorts of things that you could never calculate before, which now you can. Like, for instance, now you can actually predict the heat capacity of things. Right? You remember what the heat capacity is. It's like how much energy something takes in to change a bit of temperature. And there isn't, before statistical mechanics, there was just sort of no idea. I mean, if you say, look at physics in 1860, ask how would you calculate heat capacity, no one would know how to do that. And now you can. Well, one of the basic applications is actually something you probably haven't heard of. Again, it's the light that's emitted by a hot object. In fact, I'm going to show you the spectrum of light emitted by the sun. But in fact, all objects are at least somewhat hot. We're hot. We emit light in the infrared. You guys have probably seen videos or at least pictures of people in the infrared, right? And your face is glowing and your clothes are shielding it a bit and you're a little bit cooler, right? And in fact, for reasons that we'll talk about later, we actually talk about objects that are emitting light as being black bodies. So you should be able to calculate how much light. I mean, we know about light from Maxwell's equations, but this is a different question. The question is, I just have a big thing, it's in some temperature, what's sort of the average emission of light? And that turns out it's all about the statistical approach. It's not a kind of a mechanical thing. You're not asking some detailed question about this atom emitting some light or something. It's more just an average type of argument. And you should use statistical mechanics. And it turned out that they couldn't get the calculation to work out at all. It failed utterly for the higher energy photons, right? So, we know that, different color light corresponds to different color of light. What did I say? Different color of light corresponds to different energy of light, right? So blue photons are higher energy than red photons. But, okay, forget blue and red. There's ultraviolet photons, which we can't see. They go right through your eyeball. And they're higher energy still. And then there's X-rays, and they go right through your head. And there's gamma rays, right? And they're even higher energy. On the other side, below, normal light, there's infrared, which is sort of a really long wavelength, and our eyes aren't sensitive to it. Some animals see it a bit, and et cetera. And you got radio waves, et cetera. Okay, so there's all sorts of light, and you have to work that all into this theory, which we'll actually work out a little bit later in the class. And it just totally failed. This was the so-called ultraviolet catastrophe because basically the theory predicted that there would be an infinite amount of light at a high energy from like any object. Like just if you tried to ask, what's the light that's emitted by a person at room temperature? And the answer was infinity. And this guy Planck, German, by the way, if you ever go to Germany, if you ever continue in science, There's a whole set of very prestigious institutes in Germany, the Max Planck Institutes, because he made a huge contribution. Turns out he did it by introducing sort of a kludge, flat out a kludge. He had no theory behind this. He just noticed that if you're working with the mathematics of all this stuff, if you say that, well, sorry, and to back up, for Maxwell's equations, everyone thought light of kind of this continuous wave, and they were using that idea behind how they did the statistical analysis of how much light should come off, right? It's a wave. Everyone knows it's a wave. I mean, Maxwell's equations, this is triumph. It's got to be a wave. And he said, well, for some reason, when the light is emitted by an object sort of randomly, even though it's a wave and it could be any energy, let's just say that it only comes off in little discrete bits at a time. And I don't understand why. It must have something to do with the emission process. And it turns out if you do that, you can get the calculation to work out. And it's spectacular. Let me give you two examples. There's two curves. Apologies, that's old school. It's black and white. Wavelength is going over to the right, so energy is going over to the left. Right? Longer wavelength light is lower energy. And this is some measurement of how much light, the spectrum basically, of the sun. And there's two curves, both black and white. One is kind of jaggedy, that's the data. And the other is the curve, which is the predicted amount of light versus frequency for the sun with no free parameters. It's just assuming the sun is this quote-unquote blackbody, which, you ought to at least know something about what the sun's made out of. No. The statistical mechanical approach, there isn't anything like that. And it turns out, except for some details, which are the fact that because there's certain atoms, it's not quite a quote-unquote blackbody, and we'll talk about what that means later, but just this idea that the statistical approach has this incredible ability to correctly predict the light from the sun. Imagine that. This very mathematical, statistical thing, that weird equation on Boltzmann's gray, from that, we calculate the color, the light versus frequency for the sun. And it works. Works super well. And by the way, so this ultraviolet catastrophe was that the predicted curve went something like that without Planck's little assumption that the light is somehow coming out in little packets. There's another thing. I know you guys have heard of the Big Bang. Big Bang is, is an amazing result. The fact that you look at the universe, it looks like there was a Big Bang. One of the key cornerstones of knowing that there really had to have been a Big Bang is that if there was a Big Bang, then there had to have been sort of a fireball, just like the color of a flame. There was a point in time when the Big Bang, everything in the Big Bang was basically the temperature of a flame, literally a normal old flame. And it should have been emitting light, and that light should have been treated fully by statistical mechanics, and it should have had a quote-unquote blackbody spectrum, basically this spectrum. Now here it's drawn the other way, where energy is going to the right because it's frequency going to the right. Sorry, different fields have different conventions. They don't plot wavelength, they plot frequency. And that glow of light left over from the Big Bang has been measured extremely well. Turns out this is the best measured blackbody spectrum of anything ever. Okay? And I've put theory and data on top of each other, and I could expand, I could zoom in on this curve, and you couldn't find the difference between the data and the theory. It's that well measured, and it's that exactly corresponds to a blackbody spectrum. And any attempt to say there wasn't a Big Bang has somehow to deal with that. The best measured spectrum of a blackbody ever, I believe, I could be wrong about that, but I've heard it said, is of the light from the Big Bang. And it matches the theory just beautifully. Okay, so that gets us to quantum mechanics, or we're getting to quantum mechanics. How do we get to quantum mechanics? Well, there were these hints from statistical mechanics. Planck had to say, oh, well, the light pops off of things in little packets. And it turns out in this, when I said, let's count the number of states, remember when I talked about this number of states? And I said the example is how many different ways you guys can arrange yourself in the chairs? And when I said the number of ways you can arrange yourself in the chairs, there was the notion of a chair. I mean, what if I could chop you guys up into little pieces and you could sit in, the bits of you could sit in chairs of arbitrarily small size? Then there would be no end to the number of ways you could sit. If I want to count the number of ways a system can be, fundamentally I've kind of got to have the notion of some irreducible size at which I count. And that was kind of built into statistical mechanics. And of course, Boltzmann had no idea that this was going to lead to quantum mechanics. But he was introducing sort of an arbitrary cutoff size. He was kind of embarrassed about it. It was one of the failings of the theory. Turns out that predated it was a hint that there was quantum mechanics coming in that. There's something called the photoelectric effect. Have you guys heard of that? It's a simple thing. If light hits a material, it can kick an electron out, okay? Doesn't always happen. It depends on the materials. Often the photon goes deep in and an electron doesn't get out. It'll almost always excite an electron, but if it does it right at the surface, the electron can pop out. And the classical expectation, since light is a wave, you say, oh, well, there's energy in a wave. And you might remember there's energy in electric fields. Remember it goes like E squared? Or in magnetic fields, it goes like B squared. Or in a wave of light, there was, have you guys remember the pointing vector? I'm not sure you would have seen that. But anyway, there's energy in the light, and it's basically energy squared and magnetic field squared. And so the electric field can take on any value, and the magnetic field can take on any value. So you'd have thought that, that the intensity of the light is just proportional to those. And so basically, if you have more light, it's sort of like more electric fields, you ought to have a higher energy. Anyway, the measurements, though, didn't work out. And we'll go into detail about this later. But basically, if you have a material and you shine light on it, if you turn up the intensity of the light, you might think you're going to kick out the electrons harder. They'll come out with more energy. Turns out that just simply doesn't happen. Turning up the intensity of the light is sort of ramping up these terms. But that doesn't make the electrons come out harder. It makes more electrons come out, but they come out with the same energy. And so it turned out that the missing idea was that while this is somehow a measure of the overall energy in a beam of light, if I have a laser and I want to, James Bond style, I want to get you, or you want to carve something up, or lasers are used to cut metal nowadays. This is the right way to think about things, but it's missing a key idea. The idea it's missing, which fit into what Planck said, and which explains the so-called photoelectric effect, was supplied by Einstein, who later came to not believe in quantum mechanics, but it was supplied by him. He suggested that what was going on is that light actually fundamentally, while there's somehow this type of energy associated with it, there's itself, though, the light is broken down into little particles, now called photons, okay? And those particles have a given energy that's got in little bits. And this he predicted in 1905. The same year he came out with special relativity. And so in this Blackbody spectrum thing, where Planck had said, well, I don't understand why the light would come off in little packets. Let's just say that's about the emission process. Einstein said, no, the basic idea is that light fundamentally is generated in little individual particles. If you have a lot of light, a flashlight, a light bulb, there are so many photons that for all practical purposes, this distinction is lost. And it was invisible. People didn't know about it. If your eyes are incredibly dark adapted, they've done experiments, your eyes can see a photon at a time. They'll put people in a dark room and they'll arrange conditions so that only like one photon is appearing on the screen every few seconds, and they'll ask people to speak up when a photon hit. And they've been able to determine that people see individual photons. So light fundamentally actually comes in individual packets, okay? And the energy of those packets has this number h, which Planck had to introduce to do the Blackbody spectrum, times the frequency. Okay? So the light was quantized, broken into packets. And that was the thing that really broke the door, knocked down the door and broke things open for quantum mechanics. So what are the key features of quantum mechanics? Let me list them here and then go through them. Get all of them up. No. Quantum mechanics is what we're going to spend a lot of time, probably the most of the time in this class on. And it's, it's a very strange world. the energy of particles and the momentum of particles exist in these weird quantized states. You can't have any old energy. You can't have any old momentum. Only certain values are allowed in many situations. There are situations where that's not true, but in many situations that's true. Whenever the particle is kind of stuck, then it has only certain energies. The actual knowledge of particles is probabilistic. This is the part Einstein objected to. He spent the second half of his life actually railing against quantum mechanics. He said, God does not play dice. But in fact, nature apparently does. So if in quantum mechanics, if I'm going to have something happen, and in a real quantum mechanical system, well, real quantum mechanical systems are small. That's why it's not intuitive to us that things would be probabilistic. If we try to make examples on our normal scale, things all seem very, very strange. But of course, quantum mechanics doesn't apply to big things. But if it did, then you get all these weird statements. It would be something like, if I'm going to walk at this table, I've got a 50-50 chance of going around the table that way or that way. And it's only random as to which will happen. And you can't predict that I'll go around that way or go around that way. And classically, I'd walk right into it and get hurt. But quantum mechanically, I'm actually going to walk around it. Okay? There's all sorts of bizarre things like that. In the syllabus, there's a couple of books. There's some fun books we recommend. There's lots of fun books about quantum mechanics. There's a real old school one by George Gamow from the middle of last century. And he talks about having your car in the garage. And after some time, there's some finite probability that the car is quantum mechanically hopped out of the garage. I mean, it's incredibly unlikely to happen. It won't happen in the age of the universe. But in principle, it could. It's a quantum mechanical effect. Okay? So where things are and how they behave is probabilistic. And there's this thing called the wave function, which gives us the probability of something. And the whole goal of quantum mechanics is to find the wave function for a particle. And then you can calculate how it might behave, or it will behave, but only in a probable way. And that's all you can do. You can't say the particle is there. We don't know where it is. It builds in these things you may have heard of, the uncertainty relations, Heisenberg uncertainty relations. Momentum and position are fundamentally, inextricably linked in a sort of dual sort of way. So if I know where something is exactly, then I have utterly no idea what its momentum is. If I know the momentum of a particle, the only particle whose momentum I can know exactly is a particle which is spread out throughout the universe infinitely. Okay? If I make the particle sort of be in a space like that, then its momentum will be uncertain within a certain reasonable amount. Okay? Similarly, energy and time. If I know when a particle is, then I have no idea what its energy is. Conversely, if I know the energy of a particle, then I don't know when it was. Okay, and that's bizarre. And then there's this last thing, which I'll just list here, just to convince you, if you're not already, that quantum mechanics is weird. Particles that have a spin, which means basically electrons are sitting there, and in some sense they're like spinning, or neutrons or protons, that is quote unquote integer as opposed to half integer, have totally different behavior. Okay? And I don't know if that means anything to you, but I hope to get you to where you understand what that statement is by the end of the class, at least by the end of the quantum mechanics section. Okay. So we only have a few minutes left. Oops, I zipped past this. There's special relativity. Go a little faster here. Speed of light is a puzzle. As I've said, light is explained as an electromagnetic wave by Maxwell's equation. And in Maxwell's equations, if you remember, the speed of light pops out. It's the square root of, I'll get it wrong, is it epsilon, mu naught over epsilon naught, I believe, right? And that's the speed of light. But isn't that weird? How can you have a speed when I don't have a frame of reference? If I turn on a flashlight and it emits a beam of light, and then I'm running along and I turn on a flashlight, shouldn't the light go faster? Any normal thing would be like that. If I'm going to throw a ball and then I start running and I throw the ball will go faster. There's no notion of even a frame of reference or anything in Maxwell's equations. So it's just this kind of weird thing. And in the late 19th century, people, boy, this was quite a hunt. They just said, oh, there's an ether. There's an ether. whatever that is. And if they want to be fancy, they said it was AETHER, okay? And the electromagnetic waves propagate in the ether, and the ether is all through the universe. And light travels at the speed of light with respect to the ether. So therefore, if the Earth is moving through this ether, then the speed of light ought to be different because of the motion of the Earth through the ether. Okay, and we'll talk about this tomorrow or Wednesday. That turned out to be total bunk. An experiment that proved it was Michelson and Morley here, this university, okay? 1887. There is no special frame of reference. And so then you lead to all of special relativity. And we're going to spend the next 2 weeks talking about it, so I'm going to say very little here, except that as you may know, special relativity is very strange. Space-time is a four-dimensional continuum. Space can bend, time can bend, and then mass and energy are equivalent. Who knew that would come out of thinking about Maxwell's equations hard? But it did. It did. E equals mc squared came out of Maxwell's thinking about Maxwell's equations very deeply. In fact, the title of Einstein's paper was about electrodynamics and blah, 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 blah. Okay? We have 5 minutes left. So what does this get us to? I said at the beginning of the lecture, one of the things people didn't understand that maybe they should have stopped to think they didn't understand is what powers the sun. There's a great historical story here too. So the sun outputs this huge amount of power, 4 times 10 to the 26 watts, right? A kilowatt, which is a hairdryer, is 10 to the 3 watts. A megawatt, which is a lot, is 10 to the 6th. A gigawatt, which is sort of a large power plant. You know, that's a city, I think, takes some number of gigawatts, okay? Is 10 to the 9. Well, the sun outputs 10 to the 26. A huge amount of power. Where does that power come from? Oh, also I should mention there's these particles called neutrinos, which the sun is outputting a gigawatt neutrinos all the time. And you didn't even know that. There's like 100 million go through your body every second from the sun. We'll come back to those later. Well, people thought, okay, well, to the extent, okay, so now physics is developing and people start to have some confidence. I mean, in the 1400s, if you said, what powers the sun? You know, but by the late 19th century, it's a reasonable question. You've got all of classical mechanics, you've got E&M under your belt. Let's ask the question. One estimate is gravitational energy. In other words, we don't know how the sun formed. I don't know if you've ever thought about this, but like suppose the sun starts to form out of some gas cloud. And there's a little clumpiness there, and more stuff starts to fall on where there was a little more clumpy, there's a little overdense a clump. It's gravitationally attracts other things, and pretty soon the gas starts to accrete. And that is how the sun and planets form. When the stuff falls down into the gravitational potential, if you think of it that way, or in other words, just if something's going to get stuck on the sun gravitationally, when it hits, it goes kersplat, and there's a lot of energy there. And if you add that all up, all the kersplats, it turns out it's a ton of energy. 10 to the 41 joules. Darwin, well, but the thing is you say, well, okay, but if it's putting out this power, just divide that power watts by this many joules by that many watts, seconds. That seconds is 19 million years. And Darwin had just come up with the special theory of, he'd written this Origin of the Species, and actually in one of the first editions he tried to think about, well, was there time for evolution? And he actually went and did some good geology, or maybe he talked to geologists, I'm not sure the story, but he thought about erosion in this one formation in England and concluded that that erosion was so slow that that said the Earth had to be 300 million years old. And so, yeah, that's some physical sort of correlation that sort of agrees with the idea that you might have evolution. Thomson, an extremely brilliant physicist, later Lord Kelvin, had a huge amount to do with the development of physics at the time, didn't like evolution. So he tried to pick holes in this. But they really kind of were in an impasse. Then radioactivity came along by Rutherford and others. One thing, and we'll talk about this later, is radioactivity was the first time you could do accurate dating, much more accurate than estimating erosion. And they showed immediately that the Earth was on the order of 1 billion years old. The second thing is that radioactivity was measured in the form of alpha particles coming out of atoms. Atoms were breaking apart and decaying. They did not understand the energetics, they did not understand the origin, they didn't understand what this was as an energy source, but they could see it. And that amount of energy was in the right scale to be the power in the sun. And in turns, that is, so this is basically the right idea in general, but wrong in detail. So the true source of power of the sun is the nuclear energy that Einstein later figured out. And then there's some details about exactly how it works out. We'll try to get to, I'll mention that briefly later in the semester. Let me just have one last slide. I think it'll be fun. We have about 3 minutes left. Let me do this one last slide. So that takes us to today. There's particle physics, which is if quantum mechanics isn't weird enough for you, and special relativity isn't weird enough for you, let's combine the two. And you get weirdness squared, and that's modern particle physics. And let me just give you one little hint, and this will really be the last thing I'll say, and then I'll list some other things and we'll stop. This is a modern, it's called a Feynman diagram. You may have heard of Feynman. He's one of the great physicists of the 20th century. If you have a photon scattering off of an electron, this is the modern subatomic view of what happens. And this is called the Feynman diagram. Very deceptively simple diagram. It seems like it's just I'm drawing little squiggles, but it turns out there's a lot there. Time is running to the right. A photon comes in and an electron comes in. It turns out the photon is fully absorbed in the electron in a way that's been worked out using quantum mechanics and special relativity. The electron continues on its merry way, then emits a photon again, and then continues on its merry way. Fine, fair enough. It turns out, though, each and every time a photon scatters on an electron, there's a combination of two processes which happen in a probabilistic quantum mechanical sense at the same time, okay? And the other process happens almost backwards in time. The electron is cruising along, and all of a sudden decides to emit a photon and continue on its way. And that violates energy conservation. And it does it because for some short indeterminate amount of time, delta t, I said time and energy had an uncertainty relationship. For a short enough time, I can just borrow energy out of nothing. The electron does, it creates the outgoing photon, continues along its way, then it absorbs the incoming photon, reestablishing energy conservation, and then continuing on its way. And so there's this time-ordered process and this time through the looking glass process that both happen, and they're equally valid, and we don't know which actually happened when the photon bounced off of the electron. And that's kind of a taste for how weird modern particle physics is. And then all of this figures into cosmology. There's condensed matter physics, nanotechnology, atomic physics, etc. And that's what we're going to be talking about the rest of the semester. Okay. You send me an email or no? Yeah. Your name is? Huh?
DNDRI.
Okay. So yeah, I haven't dealt with a couple.